Hi, Cassidy.
Hi.
You weren't here on Monday or Tuesday, were you?
No.
No, it's no big deal. I just wanted some sense of where I ended. And I believe I ended at formal charge or something like that. Okay. I'm a little behind, so I got to get going on it. Have you looked over this stuff, Cassidy?
I have not, but I think I'll understand it just based off the quiz this morning. I didn't struggle too hard, so.
Okay. Basically, do you know how to do Lewis dot structures?
Yeah.
All right. What I went over on Monday is the fact that you can violate the octet rule.
Okay,
Okay.
yeah.
All right. So something like, okay. Something like, I'll give this for an example. All right. If this compound exists, XeF4, that
Mhm.
exists. All right. In order for me to draw a Lewis dot structure of it, though, fluorine can't have more than 8. Xenon can. So the extra electrons have to go around the xenon, which means the xenon in this particular instance has 2, 4, 6, 8 bonding and 2 lone pairs for a total of 12.
Okay.
Okay. So we're going to go up to 6. I don't believe there's anything beyond 6 in terms of compounds having the center atom needing more than 12 electrons.
All
Hi,
right.
Jasmina.
Hi, how are
I'm
you?
just doing a little bit of review. Now, the reason for that, Cassidy,
Uh-huh.
do you see the elements that are on the third level?
Yeah.
Okay, if you're in the n, if the n equals 3, that means you can have d, p, and s electrons. So the third level does have d orbitals. Second level does not. So anything beyond the third level, these compounds can accept more than 8 electrons. Does that make sense, Cassidy?
Yeah, it does.
Okay, there are other examples. The compound BeH2 or BeF2 exists. Okay,
Mm-hmm.
it does exist, but BeH2 only has 4 valence electrons. So if you go to draw the molecule, then beryllium is not going to have 8 around it. Can't.
Okay.
And the third example is something called a radical. If you try and draw something like NO2, NO2 has an odd number of valence electrons. So one of the electrons becomes unpaired. It's a special kind of compound known as a radical. It's very, very reactive, but it does exist.
Okay.
So we went from that. We also did something called formal charge. And when you have more than one way to draw a molecule, okay, you settle on formal charge. I'm trying to find trying to find my formula page and I'm not finding it. All right. Formal charge is equal to normal valence electrons. Okay.
Mm-hmm.
What you're trying to do is you're trying to compare the electrons around the atom in the molecule versus that atom if it was just free. Okay.
Okay.
And the way you do that is write this formula down. Formal charge is equal to the normal valence electrons. If you look in the periodic chart and you determine what the valence electron should be for that atom outside of the molecule, that's what the normal valence is. Minus the lone pair electrons around that atom in the molecule. If we're dealing with CO2, the number of lone pair electrons, 2, 4. Okay.
Okay.
So it's the normal valence electrons minus the lone pair electrons plus the bonding electrons divided by 2. And the reason you divide it by 2 is those electrons are shared between 2 atoms. So in this case, if I'm dealing with this oxygen, the normal valence electrons are 6 minus 4 lone pair electrons plus there are 2 bonds, so there are 4 bonding electrons divided by 2, or 6 minus 4 plus 2, 0. If I'm dealing with this oxygen, oxygen still has 6 normal valence electrons, but now it only has 2 lone pair electrons plus 6 divided by 2 bonding electrons. So you get 6 minus 2 plus 6 divided by 2. That's why the formal charge on oxygen is a +1.
Okay.
Does that make sense to you, Cassidy?
Yeah, it does.
Then overall, you look at the molecule with the least amount of formal charges on it. I'm not talking about adding them. I'm talking about looking at the individual atoms and seeing if they have charge on them. Because if I add all of these, it's going to add up to 0, just like this one does. But if I want to know which the best structure is, can you see that this one has more atoms with charge on them?
Yeah.
Okay, if that's the case, the compound that has the more formal charges is the least stable. You want to go with the other one. That's the first rule.
Okay.
The second rule is if you have a negative charge, you want to make sure that the negative charge is on the more electronegative element. Okay?
Okay.
Say I was dealing with COS and I put the S over here. That would mean that my S would have a -1 charge. All right, Cassidy?
Okay.
And I'm comparing S with O. O is more electronegative, so that is not going to be the more stable compound. Does that make sense to you?
Yeah.
And that's basically what I did on pretty much on Tuesday. Right, Jasmina? Jasmina?
Yeah.
Is that where I ended with formal charges?
Yeah, it is.
All right. Okay, girls, we're going to go through and do resonance real quick. We're going to do resonance real quick, and then we're going to do polar bonds real quick. Then we're going to get into more thermochemistry, unfortunately, for you. All right. If I draw an ozone in Lewis dot, it looks something like this, correct? Say yes.
Yes.
All right. Is there any special reason I put the double bond on the right oxygen? Could that double bond be just as easily on the left oxygen? Is there anything that makes the right oxygen special?
It has no.
There's nothing special about it. I could just as easily make the double bond here. Okay, resonance involves double and triple bonds. Okay, if you can manipulate a double or triple bond within the molecule and come up with an equally legitimate Lewis dot structure, you have resonance. And it makes the overall molecule that much more stable. Okay. Now, we're going to get into this probably in a couple days, and we're going to get back into resonance in a couple days. But ultimately, the thing that makes double bonds are the atoms having free p orbitals. The p orbitals are the ones that make the double bonds. So this has a p orbital that's free, this has a p orbital that's free, and this has a p orbital that's free. All right. Since the double bond has an equal chance of being in either place, the electrons kind of get spread out amongst those p orbitals so that you get a spreading out of the electron density. And really what happens is that you get a stronger molecule. The other reason we know that this exists is if this existed as having the double bond either on the right or the left, the bond with the double bond would be shorter than the one with the one on the other side with the single bond. If we look at the molecule, the bond lengths are the same. So this is further proof that this phenomena is happening. And what's really happening with resonance is you're getting a blending of all the electrons, much like if you took yellow and blue paint, shove them together, and you get the green. That's basically what's happening with these molecules. You're getting this flow of electrons throughout the entire molecule, which makes it much more stable. Okay, again, if I have something like the carbonate ion, there's nothing that says, I'm sorry, this ion, the acid functional group. There's nothing that says that the double bond has to be on the horizontal oxygen. It could just as easily be on the vertical oxygen. And again, what happens is these electrons get spread out. That process is called delocalization. Now, if I have another, I'm going to draw something real quick. Let's do this. Okay, I have carbon dioxide. Is there any way I can manipulate these double bonds?
Not that I can think of to keep an octet around carbon.
No, you can't really. You can't really because of the fact that you could put a triple bond and a single bond. But as I just showed you, that compound is not as stable as this one. So it's going to exist in this form with the double bonds, but I can't take and shove these double bonds with one another. Okay, does that kind of make sense, guys?
Yeah.
So if you can manipulate the double bonds such that you get an equal Lewis dot structure, then you have resonance, then the molecule is a little more stable. Okay. Basically, what you do here is you can figure out whether or not these have a possibility of resonance. I'm going to draw a couple of them. And I'm going to draw a couple of them real quick. I'm going to stop the share and get to here, go up to the whiteboard. Okay, if I have SeCl2, Se has 4, Cl has 7. So I have a total of 18 electrons. I think Se has, sorry, I better look it up. Don't ever depend upon your memory. I was wrong. Se has 6. And chlorine has 7. So I have 20 total, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Does this have any possibility of having a resonance? Are there any double bonds?
No, but you can create them.
How can I create them without giving chlorine extra electrons? If I bring this double bond in here, doesn't that mean that chlorine has 12?
Oh, yeah.
Or 10
I
rather?
would say, okay.
So you
Chlorine
can't
would
have,
have selenium.
what's that?
Wouldn't chlorine still have the same amount if you move that bond and then selenium would have had more?
I'm taking this one away. I'm putting here, right? Selenium would still have 8, but
I thought
chlorine,
you meant from chlorine, sorry.
okay. Then selenium would have too many. Selenium 2, 4, 6, 8, 10 now. Okay, Cassidy?
Uh-huh.
So this can't, you can't make a resonance structure out of this one.
Okay.
But if I have ClO4, Cl has 7 oxygens, 4 oxygens have 24, plus the extra electron, that is now 32. Hold on a second, guys. I got to see something. That actually is, if we count them, that is 32. So can this one have resonance structures? Guys, you back here? Jasmina, Cassidy?
Yeah.
Can this one have resonance structures? Are there double bonds?
No, because then
Can't
fluorine would have too many.
have, you don't want to stick an extra one on there unless you have to. Okay? So that one also can't. Now, if I do CSN, this is a minus, so 5, 4 is 9, 6 is 15, and undo. So I got 16 electrons. I can draw it this way, or supposedly I can draw it this way. Or I could draw it does this have resonance?
Yes.
If I can manipulate the double and triple bonds, then yes, it does. Questions about that? We're going to go over it a little more when we get into molecular orbital theory. This is something that you're going to need if you're going on to organic chemistry. If you're not going on to organic chemistry, this is a one and done thing that you can basically kind of throw away. Clear enough, guys?
Yeah.
All right, the next thing we're going to talk about is something that's a little easier to understand, and that is polarity of bonds. And polarity of bonds is going to lead us into a discussion of the molecules being polar. Now, remember we've been talking about 3 different types of bonds. Ionic bonds, where the electron completely gets stolen by one of the other atoms. Covalent, where the electrons are equally shared. And then you have something called polar covalent bonds. Now, if you have fluorine stuck with another fluorine, both of the fluorines have the same electronegativity, so they're not going to hog the electrons. On the other hand, if I have fluorine with hydrogen, the fluorine is more electronegative. It's going to hog those electrons. So in effect, what happens is this side of this molecule is going to have a slight negative charge. This side is going to have a slight positive charge. And if I put this molecule in a magnetic field, if the positive's up here, then the fluorine end is going to drift in that direction. If the negative end is down here, the hydrogen is going to drift in that direction. So you designate polar bonds by having this little funky symbol here is called the delta. It's like the small case delta in Greek letters. If you put a plus, delta plus, that means, and delta plus and delta minus, you've designated which end of the molecule is positive, which end is negative. And it all has to do with electronegativity. If the difference is between 0 and 0.5, pretty much they're sharing the electrons evenly. Between 0.5 and 2, the one that has the greater electronegativity is stealing those electrons more. It's going to have a slight negative charge on it. Then if you go greater than 2, that means we have an ionic bond. We've completely stolen the electron. And basically you can designate it, as I said, by these little deltas, plus and negatives, or you can designate it with an arrow. The arrow, the head points where the negative charge is going. And this basically is what I just described about being in the magnetic field. That is, the dipole moment is the force aligning the molecule with the magnetic field. What I want you to basically know is I want you to be able to look at a molecule, look and see, oh, this has chlorine. Chlorine's highly electronegative when it's placed next to selenium. So therefore, there's going to be a polar bond there. That's what I want you to recognize. Carbon next to bromine. Bromine's more electronegative. We have a polar bond. Fair enough, guys?
Yeah.
Is there anything that I need to explain further, or are there any questions that you have?
I don't think so at the moment.
Okay, now we're going to get into something that's going to seem totally kaflooey. Why he stuck this here rather than in the thermo chapter, I don't know. But there are certain things that we have to understand. Do you remember when we were doing thermo and we added up the heats of reaction? Do you remember that?
Yeah.
We're going to do the same basic thing, only instead of using the entire heat of the entire reaction, we're going to use the energy it takes to form bonds. Okay?
Okay.
Now, all of the numbers you're going to get in the chart that you're given, all of those numbers are going to be positive numbers because it takes energy to form bonds. When bonds are broken, the energies are, when bonds are broken, I'm sorry. Again, I do this every time. Okay, erase what I just said. Okay? When you break bonds, it takes energy to break bonds. Okay? So you have to input energy. If you have a carbon and a hydrogen and you want them separated, it takes energy to take them away from one another. On the other hand, if you have that same carbon atom and you have an oxygen floating out here, when those form a bond, energy gets released. Sorry. Yeah, energy gets released. It is exothermic. So breaking bonds, endothermic. We put energy in. Forming bonds, exothermic. Energy gets released. And I know, I apologize for that. If it's any consolation, you've just made me make sure I do it right for the second lecture. Bonds being broken, you have to put energy in. Bonds forming, energy gets released. As I said, all of the bond enthalpies are positive. They're all positive because we're basically saying we're forming this bond. In order to form an NH bond, it takes 391 degrees or 391 kilojoules per mole. Now, if you think back to when we were doing the heats of reaction, when we were doing it with the enthalpy of the entire molecule, wasn't it products minus reactants.
Yeah.
Well, in here, when we're breaking bonds, we are literally when we're breaking the bonds, we have to put energy in. So that is a endothermic process. So it's going to remain positive. When we form the bonds, that's exothermic. We have to make it negative. So all of the numbers here are positive. So in order to make the bonds breaking be negative, we have to subtract it. I guess what I'm trying to say is, if you look at this equation and you look at the one we had before, it seems like the reverse, because these are going to be the reactants. These are going to be the products. You got to keep them straight. Questions about what I just said?
No, I don't have any.
All right, so if I have a reaction, I have 2 hydrogen molecules plus 1 oxygen molecule, making 2 waters. Okay, you got to sit and analyze what's happening. I've got 2 H's, right? 2 molecules. I have an H and an H and an H and an H. Is that correct?
Yeah.
So how many HH bonds am I breaking?
2.
2. I have 1 OO molecule. How many OO bonds am I breaking?
1.
So I'm going to take the 2 HH bonds. The energy it takes to break one of them is 436. I have 2 of them. I got to multiply that by 2. I'm breaking one of those, so I'm multiplying it by 1 times the energy it takes to break an O2 molecule. So I've got that. That is what's on my bonds being broken side. Again, those are all going to be positive. Now I got to figure out what I'm making here. In 1 H2O molecule, how many HO bonds am I forming?
2.
How many molecules do I have?
Oh, 1.
No. Cassidy,
2.
how many molecules do I have?
2.
I have each molecule of H2O has 2 OH bonds,
So 4.
but I have 2 molecules, so it's going to be 4. So when I deal with the OH bonds formed, I've got 4 of them being formed. So I multiply 4 times the 463 that it took to form those 4 bonds. So I'm adding my 2 times 3, 436 for the HH bonds, my 1 times 146 for my OO, because those were broken. From that, I'm subtracting the bonds that were formed, the 4 times the 463. I do this math out. Okay. To form 2 H2Os, it took 834 kilojoules per mole. But if I want 1 mole, if I want the energy it takes to form 1 mole of H2O, this formed 2. So to create 1, I divide this number by 2, and I end up with a negative 417 kilojoules per mole. Are we fairly solid on this?
So the real answer would be the 834 or the 417?
Depend upon the question.
Okay. How
If
would
the
they
question-
ask for it for the 417 then?
If the question asks you, what is the enthalpy for this reaction? Okay. As
Mhm.
written, it is 834.
Okay.
But if I ask, what is the enthalpy of formation for H2O? I would have to half the 834, because 834 produced 2 moles.
Okay.
Does that make sense, Cassidy?
Yeah, it does.
All right, let's go on to our second question. Okay. Jasmina, I'm looking at my CH4. How many carbon hydrogen bonds are broken to do this reaction, Jasmina?
4.
4. And the Cl?
Just 1.
Just 1. So I'm going to look at my chart. I'm going to say, okay, my CH, 413. So my bonds broken, 4 times 413 for the methane and 1 times 242 for the chlorine. All right, Cassidy. Now, how many bonds are being formed with CHCl?
3
3 watts.
bonds.
How many things are bonded to carbon, Cassidy?
2
We're dealing with this molecule.
or 4 total.
4 total. How many hydrogens are bonded to the carbon?
3
So I have how many CH bonds?
3
How many CL bonds do I have?
1
Okay, so I would multiply 3 times 413. And remember, we're subtracting the bonds forming from the bonds being broken. So minus 3 times 413 plus CCl, I've got to find it, CCl plus a 328. I also have another compound here, Cassidy.
Mm-hmm.
What bonds do I have here? And is it being broken or is it being formed?
It's being formed and it's just 1 bond.
What's the bond?
H to Cl.
HCl, I got to find that. That's 431. Okay. Now, I did something because I wasn't thinking. And the trouble is, it doesn't really matter. Because in reality, I was only breaking 1 CH bond, correct?
Yeah.
Because I only put 1 Cl in there.
Mm-hmm.
So I only have to take 1 times 413. It doesn't matter if I broke all 4 bonds and formed 3 of them back up again. I'm taking 4 times 413 and I'm subtracting 3 times 413. So ultimately, it doesn't really matter. Does that seem to make sense to you?
Yeah.
So I'm breaking 1 CH bond, which is a positive 413. I'm breaking 1 CL bond, which is a positive 242. I'm forming 1 CCl bond, which is a negative 328. And I'm forming 1 HCl, which also is a negative 431. I add all this up, and that will give me the enthalpy of the reaction. Questions here? One more example.
Yeah.
All right. I have CH4 plus O2 making CO2 and 2 waters. All right, Cassidy, in this instance, how many CH bonds are being broken?
4
So I multiply 4 times 413. They're being broken, so they stay on the positive end. How many OO bonds am I breaking?
2
How many OO bonds?
1
1. So I'm looking at OO. To the 4 times 413, I'm going to add a positive 146. I'm going to subtract from that. Remember, CO2. Do you remember the structure of CO2, Jasmina? Do you remember what that structure was?
Isn't it 2 double bonds?
2 double bonds. So I'm going to subtract 2 CO double bonds, which I look down here, that's 799. So I'm going to subtract 2 times 799. And How many OH bonds are being formed, Jasmina?
I'm sorry, can you repeat the question?
How many OH bonds are being formed when I form two water molecules?
4 total.
4 total. Each molecule has 2 HO bonds, so there's a total of 4. So to the 2 times 799, I add 4 times, where's the OH bond? 463. Do you need to see the numbers out on this, or are you good with it the way it is? Do you need to see the final
I'm good.
answers, what I'm saying?
Will you just show it just so I can put it in my notes? Sorry, I just want to.
No. So this is 4 times 413 plus 1 times 146 bracket. So those are the bonds being broken. From that, I'm going to subtract the bonds being formed, which is 2 times 799 plus 4 times 463. Okay. And somebody stole my, I hate when I steal things from myself. Okay, 4 times 413 is 1652 plus 146. That gives me a positive 1798. 2 times 799 is 1598. Plus 4 times 463, 1852. So I get 1652 plus 1798 minus 1598 minus 3450. No, that's not right. 1652
Negative 1652 as the total.
could be.
So I got 1798 minus 3450.
I love this. 1798 minus 1598 minus, what's the 4 times 463?
Let me double check. 1852.
Why am I getting 0? Why am I getting 0 for that, guys? I got 0.
Really? I just did it again and I got negative 1652. Because 4 times 413
It's 1652.
plus 146 is 1798.
Yeah, okay, that's what the problem was. Negative 1652. You're right, Cassidy.
Okay.
Any questions about this?
No.
Fairly simple. You should be able to do this.
Yeah.
Okay, I'm not going to worry about this slide. This slide's a great slide. It shows you how to, the analytical tools that are used in this. I'm not going to bother doing it at this point. Any questions on Lewis dots and the other things, Lewis dots, formal charges, resonance, polarity, or this bond energy stuff?
No.
Jasmine, you good?
Yeah, I'm good.
Okay. Now we're getting into VSEPR. And we're going to deal with the theory behind valence shell electron pair repulsion. We're going to deal with bond angles. We're going to deal with polarity, not polar bonds. We're going to deal with polarity of the individual molecules. We're going to then go on to another theory called hybridization. We're going to deal with hybrid orbital diagrams. We'll deal with sigma and pi bonding, the molecular orbital theory, which involves bonding and anti-bonding electrons. We'll deal with the bond order and predicting para and diamagnetism. Big chapter. Now, the whole reasoning behind VSEPR is electrons don't like each other. They want to get as far apart from one another as possible. So if I've got two packets of electrons and I have something in the center that's holding those two packets of electrons within the molecule, those two packets of electrons are going to get as far apart from one another as possible, which means they're going to be 180 degrees from one another. I add a third packet. Well, what that third packet does is it pushes down. Actually, perhaps this would be better. Are you seeing the screen or not?
No.
Okay. Let's go here and let me do a whiteboard. By the way, do you like the whiteboard or not?
I like it.
Okay, I have electron cloud over here. And I have another electron cloud over here. All right. These guys are 180 degrees away from one another. Now, if I shove in another electron cloud, right? This electron cloud is going to push against this one. It's going to push against this one. And yes, these guys are going to push against each other, but since they are far enough apart, the pushing isn't going to be as significant until they get 120 degrees apart from one another. Is this making some sense to you? The electron clouds want to get as far away from one another as possible. So they are going to be 120 degrees now. That bond angle is going to be 120. Now, if I shove another electron cloud in here, how many points make a plane, guys? We're going to go back to geometry. How many points make a plane?
3.
3. I have my 3 points. So you might like to think if I throw another electron cloud in here, I get something that looks like this. Which stays on the plane. Is this as far as these 4 electron clouds can get away from one another? Is that as far as they can get away from each other?
Yes.
Cassidy, you can drive my car. You cannot fly my airplane. What are you forgetting to account for, Cassidy?
I don't know. Do you have a boat?
Yeah, I'll even let you float my boat. All right. What are you forgetting? Jasmina, what's she forgetting?
Uh,
Go ahead. How many dimensions
know.
are we dealing with when we're dealing with a plane? How many
3.
dimensions? 3.
3.
Are we? What is a plane? How many dimensions are we dealing? Are we dealing with X and Y? What about Z? Does Z come into effect when we have a plane?
No.
So when we have this guy, we can build in that third dimension. And so as a consequence, it does not appear like this. In order to get them as far away from one another, if I employ the third dimension, instead of getting a square planar formation, what I have, and I'm horrible at making these drawings. What I have is I have one of these electron clouds coming out towards me. I got one that is sitting inside my computer right now. I have one going straight up. And I have one going off to this side. In other words, ladies and gentlemen, or ladies, I am dealing with 3 dimensions. And if I was dealing with a square planar molecule, that bond angle would be 90 degrees, correct?
Yes.
By employing tetrahedron, I gain almost 20 degrees. This bond angle is now 109. If it was just on the plane, it would only be 90. And remember, we want to keep these things as far away from one another as possible because they're electrons. They want to bully their way. They want to push their weight in order to get as much space as possible. Is this kind of making sense to you?
Yeah.
Okay. I'm going to stop share here and go back to the PowerPoint. So we're trying to minimize electron pair repulsions by keeping the distance as far apart from one another as possible. So whether they are bonding or non-bonding, they repel each other. By assuming they're placed as far apart as possible, we can predict what the shape of the molecule is. That's all what VSEPR's basic plan is. In order to do this, in order to do VSEPR, I got to pin down certain points so that we know what I'm talking about. An electron cloud is any lone pair of electron, any lone pair, or bonding electrons. Bonding electrons, single, double, or triple bonds count as one electron cloud because all that electron cloud from that double, triple, or single bond is in one direction. A lone pair is a pair of electrons not involved in bonding. A bonding electron are involved in bonding. So if I am looking at this molecule, I have 4 electron domains or 4 electron clouds. An electron cloud or electron domain, same difference. I have 1 from this single bond, 1 from this single bond, 1 from this double bond, 1 from this lone pair. I have 4 things around the center atom. Okay, now we also have to consider 2 things here. We have to consider the electron geometry, which encompasses lone pairs as well as atoms. We also have to realize that we have a molecular geometry. In a molecular geometry, I can tell you what the shape of the molecule is based upon only its atoms. So electron domain geometry, will tell you the overall shape of the molecule. Molecular geometry only goes for the shape according to the atoms, which are around the center atom. All right. All you got to do is count the number of electron clouds in the Lewis structure. The geometry will correspond to the number of electron clouds. So you have to draw the Lewis dot structure first. You draw a Lewis dot structure, you have ammonia. Cassidy, how many electron clouds are around that nitrogen?
3,
But you're forgetting something.
4.
You have to include the lone pair. So it has 4 electron clouds. Those 4 electron clouds will dictate the overall shape. Then we're going to have to figure out from the overall shape what the shape of the molecule is. So those are the 3 steps we're going to go through to get shapes. First, draw the Lewis dot, count the electron clouds. The electron clouds will dictate the electron geometry. The electron geometry will dictate the molecular geometry once we subtract out the lone pair electrons. So if I have 2 electron clouds, the geometry is going to be linear. 3, trigonal planar. 4, tetrahedron. Now we have to increase what you learned in intro. In intro, we only went up to 4 electron clouds. Now we know that the center atom can have 5 or 6 things around it. So if it has 5 electron clouds around its central atom, that's going to be trigonal bipyramid. 6 things around, it's going to be octahedron. And I'm going to go through each of the shapes in their way. Now, what we have to realize is if we're having real scientific instrumentation, we can't see the electrons. And because we can't see the electrons, we have to derive certain properties based upon the overall molecular shape. That is the shape of the atoms within the molecule. So, Jasmina, how many electron clouds around this?
4,
Okay. What is the electron cloud geometry?
tetrahedron,
Okay. But I've got 4 things sticking up here, 2 of which you can't see. There's 1 electron cloud over there. There's 1 over here. So I can't see them. All I can see is this hydrogen going to oxygen, going to hydrogen. And because of the electron clouds that are up here, this has been forced into a chevron or a bent molecule. Remember, when we are dealing with the electron cloud geometry, that sets the overall geometry. So if I have 2 electron clouds, that bond angle is going to be 108. 3, that bond angle is going to be 120. 4, tetrahedron, I involve that 4th dimension, bond angle 109.5. Trigonal bipyramid, we have 3 of my atoms that are on a plane. They're 120 apart from one another. I've got 1 sticking straight up, 1 sticking straight down. Those up and down are 90 away from the planar atoms. Then I have an octahedron. I have a plane in the center, 90 degrees for that, 1 sticking up, 1 sticking down. So I have all of the angles there being 90 degrees. If I have a lone pair here, what happens is the lone pairs, do you think a lone pair has more power or the electrons that are bonded to another atom? Are they free to bully things? Or Think about these 4 electrons here. Are they spending some time around this oxygen and some time around this one?
Yeah.
So basically, the lone pair has a little more power. It pushes these guys down. So we have a bent molecule. Very good slide. I showed it in the lab. I'm showing it again tonight. Okay, first of all, write this down. I probably should put this on a slide. If there are no lone pairs, then electron geometry and molecular geometry are the same. So if I have 3 electron domains, no lone pairs, 3 electron domains dictates an electron domain geometry of trigonal planar. If I have no lone pairs, I have a trigonal planar molecular geometry. If one of those is a lone pair, I have a bent. Similarly, if I have a tetrahedron and all the 4 spaces are occupied by atoms, my molecular geometry is going to as well be a tetrahedron. If one of those locations is going to be a lone pair, then that changes the shape of the molecule from tetrahedron to trigonal pyramid. And I'm going to go over all of them one at a time. This is just a nice reference for you so that you know, you can see the number of lone pairs and how it changes the shape from electron geometry to molecular. So the steps: draw the Lewis dot structure, count the number of electron clouds on the center atom. Then use that first chart I gave you to determine the electron domain geometry. Then you're going to apply the molecular geometry by considering the positions of the atoms only. 2 domains. 2 electron clouds, if they're both bonding, they push each other away from one another 180 degrees. So my electron geometry is going to be linear, no non-bonding domains. My molecular geometry is going to be linear as well. Note, guys, even if I have a lone pair, say I have something like, I can't draw it. Say I have something like C triple bond N lone pair. I have 2 electron clouds, right? Right, don't I?
Yes.
I have the triple bond and I have the lone pair. So my electron domain geometry is going to be linear, but I only have 2 things, guys. I only have the atom of the carbon and the nitrogen. That molecular geometry is also going to be linear. If I have 2 atoms sticking out here, like in BeH2, I've got 2 electron clouds. Each of them is hooked to an atom. My molecular geometry is also going to be linear. 3 domains, 3 electron clouds. That means the electron geometry is dictated to be trigonal planar. The bond angles are 120 degrees from one another. I make one of those atoms into a lone pair. That lone pair has made the molecular geometry into a bent one. 2 are bonding pairs, 1 is a lone pair. Now, from what I've been talking about so far, do you see the bond angle between the red, silver, and red there? Do you think that bond angle is going to be bigger or smaller than 120 degrees. If everything's the same, those bond angles are going to be 120 degrees. If I put a lone pair out there, does that make that bond angle more or less?
More.
Jasmina? Jasmina?
I'm not sure.
Unfortunately, Cassidy, it's going to make it less. Because remember what I said, lone pairs have a little bit more power than bonding electrons. So it's going to push those two red balls down. If it pushes those two red balls down, that makes the bond angle slightly less.
Okay.
Summary slide. 3 domains. I have trigonal planar electron domain. If none of them is if there are no lone pairs, the molecular geometry is also trigonal planar. If I have one lone pair in there, I make a bent molecule, and the bent molecule's bond angle is going to be smaller than the trigonal planar where all 3 atoms are the same. Okay, riddle me this. All right, say I have I'm not going to go there. I'm not going to, there's something else I didn't think about off the top of my head, so we're not going to go there. Okay, just explain that. Explain that. Now, we get to 4 domains. I look at my chart. I realize that 4 electron clouds mean tetrahedron. Tetrahedron pushes things away so that the molecule looks like this. The bond angle is 109.5. Now, if I make one of those atoms into a lone pair, I go from a tetrahedron to having this 3-sided pyramid down here, which shape is a trigonal pyramid. Understand that the electron domain, the electron geometry for each of them is tetrahedron. The molecular shape is tetrahedron, trigonal pyramid. Again, now Cassidy, bond angles of these guys, more or less than the bond angle of the tetrahedron?
Less.
Very good. Very good. It's if you have a lone pair of electrons, it's always going to push down stronger than it gets pushed back. So in actuality, when you have this molecule, the bond angle goes to about 107 degrees. Can I take another, pluck another one of these atoms away from this and put another lone pair on here, Cassidy?
Yeah.
Certainly can. And when I do that, I get a bent molecule because all I'm seeing is the white to the red to the white. And because I have 2 lone pairs out here, that is even more force down there. So this bond angle is even smaller than the trigonal pyramid. Questions?
No.
All right. I have 2 different bent shapes, don't I? Don't I?
Yes.
So if I have a trigonal planar bent molecule, or I have the tetrahedron, which bond angle is larger?
The trigonal planar.
Why? 2 reasons for this.
Is there a lone pair on it?
There's a lone pair. How many? This has how many lone pairs?
2,
Nope,
1.
has one because it's trigonal planar. Only has one more spot for a pair of electrons. This only has one. How many does this have?
1.
This is tetrahedron, Cassidy.
Oh, 2.
So it has two. So this has more lone pair power, pushing them closer together. The other reasoning is, what did this start out? What was the bond angle when this started out?
90.
Nope.
I couldn't tell you.
There are three things here. Remember, a full circle is 360, three bonds
90.
is 100, no, three bonds, not four. The whole thing around the circle is 120. So if we have that divided by 3, each of these bond angles starts out at 120.
Okay.
This started out at 109. Okay. Now, summary sheet. 4 things around the center atom. We have a tetrahedral design. If none of them are lone pairs, we have a tetrahedron molecule. If we have one lone pair, we go from a tetrahedron to a trigonal pyramid. 2, we go from a tetrahedral to a bent. Some other things to consider. If you have an oxygen out here that has a double bond, and you have like 2 chlorines sticking down here, and this is a very bad molecule, you know this is mustard gas. It's phosgene. So when you have a double bond here, that means more electron densities are around this side. So it pushes down more than these push back. So that forces the bond angle to be a little bigger when you have the oxygen out here as opposed to the chlorines. Do we need practice on this, or are you okay?
I'm all right.
Jasmine, are you okay?
Yeah, I'm good.
Okay, now this gets into new stuff. If we had 5 things around the center atom, 5 electron clouds, that distributes them into 3 equatorial pairs. In other words, you get 3 in a plane 120 degrees apart from one another. And then you get one going up, one going down. So if you kind of like look at this, it's kind of like a trigonal pyramid on top of a trigonal pyramid. Hence the name. We have axial, which means the ones that are going up and down, and we have equatorial, the ones that are on the plane. When we go to replace these with lone pairs, the equatorial get replaced first. So if I have 5 things attached to my center atom, and one of them is a lone pair, remember, this forces these things down. And so what happens is it forces these things down, which makes a bigger bond angle than the 180 predicted. And these guys all will be about 116 degrees from one another. If I have 5 electron clouds around my center atom, no lone pairs, I'm going to have trigonal bipyramid shape. 5 electron pairs around there, and 1 is a lone pair. The shape is called seesaw. And if you kind of like see this, you can almost see a fulcrum between these three. Okay, the bottom one and the one that's coming around. You can almost like see a fulcrum, and it kind of goes seesaw. Some chemists have more imagination than others. If I have two unshared pairs, I get something that is called a T-shape. I've taken away, this is an equatorial. I've taken away the other two equatorial sites and made them into lone pairs. At that place, I've only got something that looks almost like a T. I have three unshared pairs, three lone pairs. That means all three of the equatorial sites are taken away. I have a linear molecule. So if I have an electron domain geometry, 5 clouds, that gives me trigonal pyramid. No lone pairs, trigonal pyramid. 1 lone pair, seesaw. 2 lone pairs, T-shaped. 3 lone pairs, linear. So it goes from 5 shared, no lone pairs, 4 shared, 1 unshared, seesaw, 3 shared, 2 unshared, T-shaped, 2 shared, 3 unshared, linear. And I got about 2 minutes. I can get through octahedron. If I have 6 pairs around the center atom, 6 electron clouds means an overall shape of octahedron. If each of them repel equally, the bond angles are going to be 90 degrees. But if I take away one of these atoms, what I end up with is something that looks like a pyramid with 4 sides. That's going to be a square pyramid. I take another one away. I make a square planar. So the octahedron, if I have 6 electron clouds, this dictates octahedron, no lone pairs, octahedron. If I have 6 domains, octahedron. If one's a lone pair, square pyramidal. 6 domains, 2 of them, I get square planar. Okay. 6, no unshared, octahedron. 1 unshared, square pyramidal. 2 unshared, square planar. All right. I'm just going to mention one more thing, and then I'm going to stop for the day. And it may actually be the end of this slide. Nope. Nope. I got to go to polarity next. All right. I have a larger molecule here, Cassidy. How many center atoms do I have?
3.
3. I've got the far left carbon. I've got the carbon that's in the center here. And I have this oxygen. I have 3 center molecules. There's 3 center atoms. So what's the geometry, Cassidy?
With 3 center atoms.
You can't answer it, Cassidy.
Okay, I was real lost on that one.
You cannot answer it unless I ask a specific question. What is the geometry about the left carbon?
The left carbon, tetrahedral,
Center carbon,
trigonal planar,
oxygen.
tetrahedral.
What specific molecular geometry? 2 lone pairs. You're right about the electron geometry being tetrahedron. If 2 of them are occupied by lone pairs, what's the shape of the oxygen?
I want to say I know it, but I literally can't think of anything else at the moment.
That's fine. Hey, you've just been introduced to stuff. How can you know it if you've just been introduced to it?
Yeah.
All right, you have two lone pairs. You have a tetrahedron. I can't draw this well. You have a tetrahedron, right?
Mm-hmm.
I can't see this one. I can't see this one. The only thing I can see are those three. What's the shape?
Is it trigonal plane? Oh, wait, no, that's the middle one. I can't see your hand. I just see your arm.
Can you see it now?
Yeah. Bend?
Bent. All right. I tell my classes, eat this every time. If you don't think well, if you can't like picture shapes in your head, all right, there are two ways you can solve that problem. One is to go out and buy a molecular model kit that run anywhere from $300 to $2,000. Okay. Or you can buy yourself a bag of marshmallows and pretzel sticks. Okay.
Do that one.
You can eat the proceeds after you're done. So that honestly, if you're not seeing this, if you can't see this concretely, then it might be a better idea for you to go out and buy yourself some marshmallows and pretzel sticks and try and put these together and take the marshmallows away and see what shape remains.
Okay.
Okay.
Mm-hmm.
All right, guys. I got as far as I really wanted to get today. I'm going to deal with polarity next, which is an important topic. Then I'm going to get on with hybridization, which isn't so bad. Molecular orbitals will blow your mind. Okay. And that's where we're going for. That's where we will be on Tuesday.
All right.
Any questions with what we did today? We did a little bit of review of Lewis dots. We went through resonance, bond polarity. We did energies of bond formations. Then we got through pretty much VSEPR. Are you understanding what's going on with the VSEPR part?
Yeah.
Jasmina, you doing okay with this stuff?
Yeah.
A lot of it is review, but there's also a little bit extra that was put in there that we don't like to discuss in intro because intro students are confused enough. Okay, guys, I will see you on Tuesday then.
Okay. Thank you. Have a good weekend.
You have a good weekend. Jasmine, you have a good weekend yourself, all right?
You too. Thank you.